So we've talked a lot about integration in two dimensions. So let's recall where we're going with this. We are trying to state and prove Green's theorem. And remember, Green's theorem relates integrals over a domain in R2 such as this circle here, or this triangle here, or this square here, to integrals over their respective boundaries. So we are going to need to talk about a little bit about the kinds of sets that show up as boundaries of reasonably nice domains in R2. And now if you look at these regions, the square, the circle, the triangle, the boundary, all those guys, their boundary looks like one-dimensional. You remember I drew the boundary without ever picking my pencil up. So you can think of the boundary as being traced out by a parametric curve. That would be a curve where that is a function from, say, a one-dimensional interval mapping to the boundary. So we're going to prove Green's theorems in regions like this, where the boundary is given by a curve, by a parametric curve. And so before we can get to Green's theorem, we're going to have to state and we're going to have to define parametric curves and talk about differentiation and integration and all those other wonderful things on parametric curves. So let's start by defining a parametric curve. I'm going to stop calling them parametric curves. In this course, a curve is always going to be a parametric curve. So a curve in RP is a continuous function whose domain is a closed bounded interval and that maps into RP for some one-dimensional domain. And now you're probably used to thinking of curves as like a circle in R2 is a curve is the set of all points x, y, such that x squared plus y squared equals r squared. You're used to thinking of a curve in RP as a set of points in RP instead of a function from the real numbers into RP. And that can be a useful thing to do in our course. Thinking of them as parametric curves, associating every curve to a function is very useful. It makes our lives easier. This is also true in courses like complex analysis, but sometimes you want to talk about a curve as a point set. So in that case, we call that the trace of the curve, which we write like this. Your book writes it the set containing gamma, which I hate which I don't like that notation. I've got the other class I'm teaching this semester is complex analysis, which writes it gamma twiddle. That's just the set of all gamma t, such that t is in the domain. So the trace of gamma is just the image of gamma, and it is a set of points. We want to be able to talk about differentiating curves, so we're going to call gamma a C1 curve or a smooth curve. If it is differentiable in the sense of definition 6.1. So if you can differentiate it in the sense that we're used to from chapter 6, at every point C in the domain, and so that's what it means to be a differentiable curve. But to be a C1 curve, a continuously differentiable curve, the function d gamma, remember this takes as input a point in the domain of gamma, and it returns outwards a linear function from the real numbers to Rp, which we saw was a vector space, if that is continuous. Now, note that d gamma of C is that is a linear operator from the real numbers to Rp, and linear operators with the domain in the real numbers, they're all of the form just your input multiplied by something. So we're going to define gamma prime of C as our derivative d gamma of C, and then we're just going to evaluate that at 1. And notice that means that d gamma of C, the linear operator, if you plug in any real number s, because d gamma of C is linear, you can pull the s out. And so you get s gamma prime of C. And it is an exercise that I'm going to leave for you. And it can be done pretty easily using theorems 6.5.9 and 6.5.7c, written in terms of functions with whose domain is one-dimensional, is that gamma prime of C is the limit as t goes to 0, 1 over t, gamma of C plus t, minus gamma of C. Now, remember, we did all that work back in chapter 6 to define derivatives without having to take any limits, without having to divide by vectors. But since our domain is the real numbers, we can go back to definitions in terms of division. And furthermore, in the sense that if either side exists, both sides exists. And the limit exists if and only if the derivative exists. in the sense you expect of our definition from chapter 6. And this mostly follows from results from section 6.5. The tricky part is to show that it also works at the endpoints. The chain rule is a useful theorem. We proved it, remember, back in section 6.5. So let's go ahead and state the chain rule in the case where one of our functions is a curve. And let's specify that it's a curve mapping specifically into some domain in RP. So gamma is a function from our interval. And let's let f be a function whose domain is V. I wanted V because I didn't want to insist that f has to have a domain all of RP, but let's let f be a function from V to, let's say, RD. Let's say that that is also continuous. Then the composition, if you composed f with gamma, that is also a curve. That is, it's a continuous function whose domain is the same as the domain of gamma and whose range is the same as the range of H. And furthermore, if C is in this interval, you have to check this. If C is an endpoint, it doesn't quite follow from section 6.5, but it is nonetheless true. And if the two derivatives, gamma prime of C, or if you want d gamma of C, you can write the derivative of gamma either way, but I've said that I want f to be a function from RP to RD, so I have to write df as a linear operator. If those derivative exist, then h prime of C exists. And you can write down what it is. H prime of C is df of gamma of C. Remember, df of gamma of C is a linear operator that takes in function in RP and spits out vectors in RD. So I have to evaluate it, and h prime of C is supposed to be a vector, so I have to evaluate this at the vector, and you evaluate it at the vector gamma prime of C. One more proposition to finish out our ideas about differentiating curves. And I will again leave the proof of this as a homework problem or exam study problem. This is essentially the product rule. So if I've got two curves, if I've got one domain in R and I've got two curves, gamma and tau, they are both curves mapping into the same RP. And let's let the function f be given by f of t is the inner product of gamma of t. That's a vector with tau of t. That's another vector. And then let's pick some point C in our domain. And let's suppose that gamma prime of t, gamma and tau are both differentiable at C. And the conclusion is that the inner product of gamma with tau, it is also differentiable at C. F prime of C, remember this is a function from the real numbers to the real numbers, so we can have derivatives back in the sense of chapter 2 from last semester. F prime of C is a real number. The real number is gamma prime of C at tau of C plus the inner product of gamma of C, tau prime of C. And in particular, it exists. So now let's move on to integration along a curve, and we'll start by asking, okay, how do we integrate the constant function 1 along a curve? In other words, what is the length of a curve? Because I don't know about you, but I think the integral of 1 really ought to be how big a curve is, which in the case of a curve is the length of a curve. So let's draw a picture. Let's let gamma be this curve in R2. Now, I don't know exactly what the length of that thing is, but I know it's certainly not longer than this, the straight line from one endpoint to another. And it's also got to be longer than this. We go straight from one end to a point somewhere in the middle and then to the other end. And it's still going to be longer than this thing where we connect up 4 points. So the idea is that our curved path from this point to this point has to be at least as long as a straight path from this point to this point. So the length of the curve, the length of the blue curve has to be at least the sum of the lengths of those yellow lines. And we know what the length of a line is. It's just the vector norm of the difference of the 2 points. So here is how I am going to define the length of a curve. Then the length of gamma, I'm going to say that is the supremum of the following set of real numbers. The set of all sums from j equals 1 to n, the length of the distance from gamma to tj minus 1 to gamma of tj. That's the length of a line segment. And then the TJs have to be a partition of the curve. So this is indeed going to get into the kind of Riemann integration we saw back in chapter 3. This is not the same definition 7.1.2 in your book. Definition 7.1.2 in the book only works for C1 curves. It involves the gamma prime, and that may not exist. This definition that I've written down, that does exist for all continuous curves gamma, at least it exists if you're willing to say that a supremum is allowed to be infinity, if you count that as existing. So L of gamma by this definition exists at least if you count infinity as existing, even for a non-C1 curve, just a continuous curve, but a non-C1 curve, such as this Koch snowflake, which is perhaps the most famous example of a curve that has infinite length. And here is an exercise, which again I'm going to leave as a homework problem or exam study problem. This is exercise 7.1.2 in your book. And that says that if gamma is a C1 curve, then the length of gamma, according to the definition I've written above, that's the supremum of these sums, is also equal to the following integral. It's the integral from a to b of, you take gamma prime of t, that is a vector, but it shows up in the definition of derivative, so that's continuous if your function is continuously differentiable. You take the norm of that vector, that gives you a real number, that gives you a nice continuous function, and you just integrate it. And that integral must be equal to the length of gamma. It's this integral, it's this second integral down here that is how your book defines the length of gamma, but I like the definition with the supremum better. And you're going to have to prove that these two definitions are equivalent, but I am going to write down a proposition from the book that you can use that will help you in doing exercise 7.1.2. Same setup, we've got a C1 curve. And we're going to pick a positive number epsilon. And the conclusion of the proposition is that there is a partition of our interval, of our domain, such that this integral of our absolute value of gamma prime minus, let's call it the length of the partition, or let's say the length of gamma along the partition. That difference is less than epsilon, where the length of gamma along the partition is just what you think it should be. It's the things that you take the supremum over in our definition of length. Let me prove this for you. So what it means to be continuously differentiable, if you unravel the definitions, you get that gamma prime, that's a function with the same domain as gamma and range RP, same range as it happens, is continuous. And AB is compact, closed bounded sets in RP, so certainly in R, are compact. So by theorem 5.5.10, gamma prime is uniformly continuous. And so let's use that it is uniformly continuous. Let's let delta be a positive number such that if S and T are two numbers in the domain of gamma prime, and they're a distance less than delta away, and because they're real numbers, remember, I can use regular absolute values, then gamma prime of S minus gamma prime of T, and notice these are in fact vectors, so I do want to take norms. This is less than epsilon, and I'm going to divide it by, I believe I want 2 times b minus a times the square root of p, all of which are positive real numbers. Let's let p be any partition of our interval AB, and we're going to say we don't want any partition, we want the partition to, in addition, satisfy that Tj is less than or equal to Tj minus 1 plus delta for all j. And since Tj minus 1 is less than Tj, that means Tj and Tj minus 1, they're a distance at most delta apart. And now I am also going to let you, or rather let our reader, pick numbers mj in these intervals, in these little intervals. So any numbers we like, we'll pick the mj's later. And now we want to write down the length of gamma, at least measured over the partition P. Remember, that's a sum. So let's let, we'll call it star sub j, be the norm of gamma of Tj minus gamma of Tj minus 1. So that the length of gamma measured over P is the sum of those quantities, star sub j. And now let's try to estimate star sub j. Star sub j, that quantity squared, let's write it like that. It's a vector, so I want to write it as a sum. I don't want to use j as a variable because I'm already using j's for the tj's. So we'll write it as the sum of gamma k of tj minus gamma k of tj minus 1. That quantity squared, where the gamma k's are, of course, the components of gamma. So each gamma k is a function from your interval mapping into. Now, by the mean value theorem, for each k, there is a number depending on both j and k in this interval that we care about. Such that gamma k of tj minus gamma k of tj minus 1, that's tj minus tj minus 1, gamma k prime of s sub jk. And now, the easiest mistake in the mean value theorem to make is to forget that your numbers depend very sensitively on which function you're looking at. So I just want to emphasize I'm calling these sjk's because they might be different numbers for different k's. And so, but we can write our quantity star j. Let's go ahead and square that. And then we can put gamma k prime of sjk. Then that quantity 2 is squared. And then notice that this is a sum in k, not a sum in j. So we can go ahead and move the tj's out front. And let me put absolute values there, not because we really need them. We're squaring a real number, but just because they don't look like parentheses. And I'm going to be writing this a couple of times. So let's let the vector vj, be gamma 1 prime of sj1, gamma 2 prime of sj2, all the way up to gamma p prime of sjp. And so we have that. Our star j, if you look at it, that's tj. Forgot to square it up here. Down here, luckily, I don't need it. tj minus 1, and then the other quantity that we're taking the square root of, that's just the norm of vj. And then we're going to break up vj by adding and subtracting, and adding rather gamma prime of mj. And by the triangle inequality, we can say that tj minus tj minus 1, then you have the norm of vj minus gamma prime of mj. Let's make that negative. Let's subtract that from the norm of gamma prime of mj. And then that's less than or equal to what we've got written above, which is our star j, and that's less than or equal to the same thing with a plus. What can we say about these little bits of errors? Well, let's compute what they are. The norm of vj minus gamma prime of mj, that let's square it. That'll make it easier to compute. We've got gamma k prime of sjk minus gamma k prime of mj. And remember again that different k's are getting different s's. So this is not the norm. This is not the norm of gamma k prime of sj minus gamma k. This is not the norm of gamma prime of s minus gamma prime of m. They depend on s in sort of a complicated way. So let's notice that each of these guys individually is less than the norm of gamma prime of sj ak minus gamma prime of mj. Each of the guys showing up here is less than this norm here, and I can't get rid of the summation yet because we've still got sjk's in here. And now sjk, it's between tj minus 1 and tj. mj is also between tj minus 1 and mk. So each of these guys individually is so the difference between sjk and mj is less than delta by our assumption. So this is less than epsilon over 2b minus a root p quantity squared. And that now we finally can sum in k, and we get epsilon over 2b minus a. The root p, you square it, turns into a 1 over p, cancels out with the summation. So let's put this all together. We can write this as, we'll put tj minus 1. And now let me put an infimum over this interval, tj minus 1 up to tj. And then our norm of gamma prime. Then we subtract epsilon over 2b minus a. That's less than or equal to the thing with our mj's. Which we said was less than or equal to our star j, which is less than or equal to, I won't write the mj things again. I will just put in a supremum. And an epsilon. All right, so let's put this all together. So let's see, negative epsilon over 2 plus the lower Darboux sum of a norm of gamma prime over the partition P. We can write the first piece as the sum of the tj minus 1 times epsilon over 2b minus a. You can check to see that because Tn is b and T0 is a, that this does indeed sum up to negative epsilon over 2. And then if you look up the definition of lower Darboux sum from chapter 1, you get precisely tj minus 1. Then there is the infimum over that interval of your gamma, of whatever you're integrating, which is gamma prime. And we have worked out that each of these is less than or equal to the corresponding star j's. So the sum must be less than the sum of the star j's, which remember we said was the length of gamma measured over the partition P. And then very similar argument. you can also get the upper Darboux sum of gamma prime over p plus an epsilon over 2. Now, we said gamma was continuously differentiable. That means that that gamma prime, and therefore the norm of gamma prime, is continuous, hence integrable. And that means there is a partition Q is such that the upper sum of norm gamma prime over Q is less than or equal to the integral of norm gamma prime plus another epsilon over 2, because the integral is the infimum of the upper sums. You can get an upper sum as close to the integral as you want. And then we can refine a partition Q that never makes the upper sum bigger. So we refine Q to a partition P as above with tj minus tj minus 1. Those all have to be less than delta. And by the above work, we have that the length of gamma over p, that's less than or equal to the upper sum plus epsilon over 2, less than or equal to integral from a to b of gamma prime plus epsilon. And there is a similar argument, and I don't have enough space on this video screen to write it down, that gives you the lower bound on L. So I'll just say we're done here, and you can work out the final details yourself. I'm going to finish up this lecture with one example about how the length of a curve is defined. So let's start out with gamma has domain 0 to 2 pi, and then gamma of t is cosine t sine t. This is the standard parameterization of the unit circle that I suspect most of you recognize. And then gamma prime of t, which we remember as an exercise, you can figure out the derivative just by differentiating component-wise. So the length of gamma prime of t is always 1, and the length of gamma is the integral from 0 to 2 pi of 1 is just 2 pi. So the perimeter of the unit circle is 1. Okay, no surprise there. Now here's where it gets interesting. Let's let rho be a function with domain 0 to 4 pi. And we'll give rho of t the same definition. And then this again is the unit circle, but in a sense, you're going around twice. You go around once, and then you go around again. And so it's still the unit circle, but because we cover it twice, the length of rho that's the integral from 0 to 4 pi of 1 is 4 pi. So length of a curve, it takes into account not just what the image of the curve is, what points you actually touch, but how many times you go over them, how many times you cross any given point. So that's why we're saying that this parameterization of a circle, this second parameterization, which is still giving us a circle, but it's giving us the circle twice, so we say it has length 4 pi instead of 2 pi.